Welcome to AI Research Weekly, the show that cuts through the noise to bring you the most impactful developments in AI and machine learning research. I'm Nova.
And I'm Onyx. This week, we're diving deep into the burgeoning world of agentic AI, not just the systems themselves, but the critical infrastructure, governance, and even the philosophical underpinnings emerging to support them. It's a fascinating shift, seeing the field mature beyond just foundational models.
Absolutely. The sheer volume of papers this week around agentic architecture's auditability and formalizing epistemic state tells a clear story. We're moving from "can it do this" to "how can we trust it to do this reliably and accountably?" It's a crucial evolution.
Precisely. And a big part of making these agentic systems reliable is ensuring they can scale effectively. That brings us to our first highlight, the AA Flow framework, a unified distributed runtime for agentic AI workflows.
AA Flow. This looks like a serious attempt to address the practical bottlenecks of building multi-agent systems, moving beyond just scripting LLM calls. What's their core innovation here?
Their key contribution is treating agentic workflows not as a series of disconnected LLM prompts, but as an operator abstraction within a unified distributed runtime. They're optimizing the orchestration and data flow across the different components of an agentic pipeline: embedding, retrieval, reasoning, memory, and upsert operations.
So less about making the LLM itself faster and more about making the entire multi-step process efficient on a distributed system. That's a significant distinction.
Exactly. They've implemented a zero-copy data plane using Apache Arrow and Cylon, which is a big deal for reducing serialization overhead. Think about how much data moves between a retriever, a re-ranker, and the generator in a complex RAG setup. Eliminating those copies dramatically improves efficiency.
That's a huge win for performance. What kind of numbers are we talking about?
They report up to a 4.64x pipeline speedup on their benchmarks, an impressive 2.8x gains specifically in the embedding and upsert phases. Critically, this is achieved while maintaining comparable LLM generation throughput. The LLM inference itself is still GPU bound, but AA Flow cleans up everything else around it.
That's impressive. It effectively means you can run much larger, more complex agentic chains with the same compute budget or achieve higher throughput for a given chain. What about reproducibility, which is often a nightmare in distributed non-deterministic agent environments?
They address that by separating logical execution from resource scheduling and employing asynchronous batching with resource deterministic scheduling. This lowers coordination costs and significantly improves reproducibility for these complex agentic pipelines. It's a thoughtful approach to bringing engineering rigor to agent development.
So AA Flow is essentially providing the scalable backbone for the kind of sophisticated agentic systems we're all trying to build. But it feels like it's aimed at the infrastructure layer rather than the cognitive architecture of the agents themselves.
You're right, Nova. And that brings us to an emerging architectural paradigm addressing the cognitive side, Omega and its memory system, myelin. This is less a paper and more a newly introduced concept, but it's a critical direction.
Omega and myelin. I'm intrigued by the concept of sovereign cognitive agents and intelligent forgetting. It sounds like we're moving towards agents with genuinely dynamic and selective memory.
We are. Omega is a layered architecture specifically designed for sovereign cognitive agents, built on a 17-crate Rust ecosystem, promising structural integrity guarantees. But the real innovation, to your point, is myelin, which is Omega's graph-native persistent memory system.
Graph-native persistent memory. So not just a flat vector store or a simple key-value cache. This implies a more structured, interconnected memory representation. And intelligent forgetting? How does that work?
myelin implements intelligent forgetting via something called the Ramanujan-Yet-Hamiltonian. This is a significant advance over passive memory management. Instead of just overwriting or expiring old data, it actively prunes and consolidates memories based on a computational model of relevance and interconnections, allowing the agent to retain what's structurally important while shedding less salient details.
The Ramanujan-Yet-Hamiltonian, that's a deep cut. It sounds like they're borrowing from physics inspired models of complex systems to create a more organic, human like memory system rather than a purely engineering driven one. But what are the implications of this sovereignty and intelligent forgetting for agent behavior?
The idea is that for an agent to truly be sovereign, it needs an internal model of its own state and history that isn't just an infinite log. Intelligent forgetting allows an agent to maintain coherence and focus by not being bogged down by irrelevant past experiences. It's about more sophisticated self-regulation and avoiding the context window overflow problem in a much deeper way than just RAG.
That's a big deal. If agents can dynamically manage their own epistemic state and decide what to remember and forget, their long-term reasoning and learning capabilities could be profoundly enhanced. But it also raises questions about auditability and predictable behavior. If an agent forgets something, how do we trace its decisions?
You've hit on a critical point, Nova, which actually leads us perfectly to the next development, Knowledge Pack 1, or KP1. This is a public draft for a format specifically for packaging epistemic state.
This sounds like an attempt to standardize how we represent and share an AI's internal knowledge and reasoning process. We've seen so many ad hoc approaches, from embedding databases to complex graph knowledge bases, but nothing truly universal.
Exactly. KP1 introduces a plain text format, organized as a directory of markdown files for packaging an AI's epistemic state. This includes claims with explicit confidence scores, evidence, provenance, and the relationships between these elements. The goal is to make it both human-readable and machine-parsable.
Human-readable and machine-parsable, that's often a difficult balance to strike. So you can open these markdown files and understand an agent's reasoning, but a system can also programmatically interrogate it? That's much better than trying to reverse engineer a black box.
Absolutely. They specifically call out the limitations of existing formats like RDF or JSON LD, which are machine-readable but not human-friendly, and context documents, which only index content without explicit epistemic claims. KP1 aims to embed that epistemic state directly within the document structure.
And I noticed they even have new semantic constraints like SC12, limiting prediction confidence to less than or equal to 0.95. That's an interesting philosophical and practical choice. Why cap confidence at 95%?
It's a fascinating constraint. It explicitly forces agents to acknowledge inherent uncertainty and avoid overconfidence. In safety-critical applications, an agent claiming 100% confidence might be more dangerous than one admitting a 95% likelihood with clear evidence. It's a mechanism to embed humility and prevent structural hallucination at the epistemic layer. It also provides a clear boundary for when human oversight must intervene.
That's a crucial point, especially as agentic systems move into high-stakes domains like scientific discovery or medical applications. Speaking of which, we have a concrete example of an autonomous agent making strides in astronomy. EGANT.
EGANT is an excellent case study in the power of well-designed agentic systems. It's an autonomous agent designed for equivalent width measurement in astronomical spectra, combining multi-void profile fitting with LLM visual inspection.
Multi-void profile fitting combined with LLM visual inspection. That's a sophisticated hybrid approach. So the LLM isn't doing the core spectral analysis but acting as a quality control layer.
Precisely. The LLM's primary role in EGANT is quality control. It confirms about 60 to 65% of the fits, flags 10 to 20% as problematic, and occasionally uses its tool use capabilities to improve edge cases. This hybrid approach allows for high precision while leveraging the LLM's pattern recognition and reasoning for nuanced assessment.
What kind of performance gains did they see? Because that's where the rubber meets the road for these scientific applications.
EGANT achieved raw agreement with human experts of a mean absolute deviation, or MAD, of 5 to 7 meters across 18,615 spectral lines. That's incredibly accurate. And the impact on workflow is huge. It reduces the time for survey-scale equivalent width measurement from months of expert effort down to days of automated analysis.
Months to days. That's a profound acceleration of scientific discovery, and they even cite a cost-efficiency metric with GPT-5 Mini at approximately 200 lines per US dollar. That's making advanced astrophysics accessible.
It absolutely is. And they emphasize reproducibility, with agreement between GPT-5 and GPT-5 Mini, and the system stores complete parameters and LLM reasoning chains for exact reconstruction. This ties back to the auditability principles we just discussed with KP1.
So we have these incredible advances in agentic systems, from infrastructure to cognitive architectures to real-world applications. But I'm reminded of a paper in the Digest with a provocative title, Autonomy is the Failure, the LLM as Autonomous Agent Anti-Pattern in the Coordination Knowledge Substrate Pattern. It feels like a necessary counter-narrative.
That's a crucial perspective to bring in, Nova. This paper formalizes the LLM as autonomous agent anti-pattern. Their argument is that when an LLM acts as an independent, unmediated decision-maker, rather than a substrate mediator within a broader system, it creates significant failure modes.
So, they're saying the very idea of a fully autonomous, unconstrained LLM agent making consequential decisions is fundamentally flawed, especially when it's just generating its own next steps.
Exactly. They point to operational forms like agent loop architectures, react patterns where steps are LLM chosen, and general autonomous task execution as examples of this anti-pattern. They argue it violates fundamental decomposition properties of what they call the coordination knowledge substrate, or CKS pattern.
That's a strong claim, but it resonates with the challenges we've seen: unpredictable behavior, hallucinations of action, and difficulty in debugging. If the LLM itself is deciding its control flow, it becomes much harder to ensure safety and reliability. So, what's their proposed architectural correction?
Their architectural correction leans into the CKS pattern, where the AI acts as a mediator of information and actions, but the overall coordination and control remains externally governed or designed. They aren't saying agents are bad, but that unmediated LLM autonomy is the problem. It highlights the need for explicit control planes, like Aegis and its evidence operating system, which also emerged this week, to mandate specific controls for every agentic action.
That makes a lot of sense. It brings us back to governance and auditability. The more sophisticated these agents become, the more critical it is to design them with inherent guardrails and transparent decision-making processes. It's about designing for intelligence, not just unbounded autonomy.
Precisely. The conversation around agentic AI is clearly maturing. It's no longer enough for an agent to just work. It needs to work transparently, accountably, and predictably within a controlled environment.
Shifting gears a bit, let's take a look at the week's Industry Watch. There have been some big moves.
A very active week on the industry front. Google made headlines with the acquisition of Wiz for a staggering $32 billion. Wiz is a multi-cloud security platform, and this move clearly signals Google's aggressive strategy to enhance its Google Cloud security offerings, likely integrating AI-driven threat detection and response at a massive scale.
$32 billion for a security platform. That's a clear indicator of where enterprise AI deployment is heading. Not just building models, but securing the complex infrastructure they run on, especially in multi-cloud environments.
Meanwhile, OpenAI closed a landmark funding round of $122 billion, pushing its post-money valuation to an incredible $852 billion. This is a massive vote of confidence, or perhaps a significant bet on the future of frontier AI models.
$852 billion. That's almost $1 trillion valuation for an AI research lab, demonstrating the immense financial capital now flowing into the AI space. It also sets the stage for what we might expect from their next generation of models.
And speaking of next-gen models, we saw reports that GPT-5 achieved a perfect 100% on AIME 2026 and holds the highest ARENA ELO score. This signifies a major leap in reasoning capabilities, especially on complex problem-solving benchmarks.
That perfect AIME score is a huge delta. It implies a qualitative shift in problem-solving and mathematical reasoning. Combined with that valuation, it really suggests that OpenAI is poised to continue pushing the boundaries of general intelligence.
We also saw Boston Dynamics Atlas robot transition from a research marvel to a commercially available product for factory work. This is a significant step in the practical application and deployment of advanced robotics, signaling a move towards more physical, agentic automation.
Atlas in factories, that's a direct connection to the agentic systems we were discussing. Real-world, consequential actions in a structured environment. And Google integrated Gemini AI into Google Workspace, allowing for automated content generation across various enterprise applications. That's mainstreaming AI productivity.
Definitely. And NVIDIA launched Ising, a new family of open-source AI models specifically designed for quantum computing. These models aim to accelerate quantum error correction and processor calibration, bridging AI and quantum infrastructure.
AI for quantum computing. That's a fascinating cross-domain breakthrough, accelerating the foundational layer of an entirely new computing paradigm.
Finally, TensorFlow 3.0 was highlighted by Google Brain, bringing enhanced usability, performance, and scalability, with improved support for distributed training and large-scale models. And a Digitimes report indicated that enterprise AI is entering a deployment phase, shifting compute architectures towards inference rather than just training.
That inference shift is key. It signals maturity, moving from R&D to large-scale operational use. It means the efficiency and scalability discussions we had with AA-Flow are becoming even more critical for real-world adoption.
This week really underscored the ongoing maturation of agentic AI. From infrastructure like AA-Flow and novel memory architectures like Omega and Myelin, to formalizing governance with KP1 and successful applications like Agent, the field is building robust foundations.
And the critical perspective offered by the autonomy is the failure anti-pattern is a healthy reminder that as capabilities grow, so must our understanding of safe and accountable deployment. The industry news perfectly mirrored this, with huge investments, advanced model releases, and a clear move toward enterprise deployment.
Next week, I'll be watching for more developments in multimodal agentic systems, particularly how the practical challenges of integrating diverse sensory inputs and action spaces are being tackled. We're seeing hints of that with Omega's design, but the specifics of multimodal reasoning beyond conventional similarity-based paradigms will be key.
I'll be looking out for how these governance frameworks like KP1 start to be implemented in practice. The theoretical grounding is there, but real-world adoption and compliance testing will be the next big hurdle. How do these abstract ideas translate into auditable, deployable systems? It's where the rubber meets the road.
Excellent points, Nova. That's all for this week's AI Research Weekly.
Join us again next week as we continue to explore the cutting edge of AI research.